Hello friends, I'll explain you at the core level why do soap bubbles have excess pressure. Now just think of a newly formed soap bubble and suppose it does not have an excess pressure, it's just formed. Now imagine a lot of surfaces inside here. Not rather surfaces, I am telling you to imagine lines of molecules which are present in this form, right? Now, when lines of molecules are present like this, then it's a natural tendency of molecules to attract each other. So the molecules which are present, suppose this is a middle line, and the molecules which are just present towards the left of it will be attracted towards the right. And the molecules which are present towards the right of this middle line would be attracted towards the left. And similarly, the molecules here would be attracted towards the right, and the molecules here would be attracted towards the left. And this would lead to the compression of the bubble. You can imagine it in this plane also. The bubble is going to compress itself. Right, and we know the gas equation PV is equal to nRT. Now, if this bubble is going to contract itself, its V is going to decrease and pressure is going to increase. And naturally, an equilibrium position will come. At the equilibrium position, the pressure inside that's pushing the bubble towards the outside. Because the pressure will increase, it will become more than the atmospheric pressure. Suppose initially the pressure was P atm, then it would become P plus delta P, right? Now this delta P pressure will exert a force on the walls of this bubble that will prevent it from uh, compressing itself more. So we are required to calculate this delta P. Now just imagine this, suppose you imagine the middle line, and or perhaps the line just towards the left of this middle line. So what's going to happen here? It's going to be attracted towards the right. The simple answer. But with what force? Now you know that surface tension force is given by S times L, right? And the length of this whole circumference is going to be 2 pi r. And we know that in a soap bubble you have actually two surfaces, one inside, or two interfaces you can say, and one outside. And we assume that this thickness is negligible, so the total force is going to be 2s into 2 pi r, where s is a surface tension of the material with which the soap bubble is made up of, right? And now the pressure inside would balance this. So if the pressure is acting, suppose here, 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 like this, the net resultant would be that the pressure is acting on this surface in this direction. I mean, it's not going to act on this surface because this surface is hollow, but the net force that the pressure will exert on the left part of this left part of the sphere or this hemisphere, if you can imagine, it would be P times pi r squared, because this total area is pi r square, and the force that the pressure is going to apply is going to be P times the surface area, and the resultant of this surface area, the surface area vectors of all these places, the ds vectors you can say, or I should use the word dA because I've used S as the term for surface tension. dA vectors of all these surfaces will result in a net surface which is given by this middle surface, or which has an area pi r square. So we just have to balance it. 2s into 2 pi r is equal to p into pi r square. The pi is going to cancel, and yes, you just have to manipulate the expression. You'll get 4s by r is equal to p, or I should rather say this p is not only p, it's delta p, the excess pressure, because the atmospheric pressure will also be exerted here. So here the pressure should not only be p, it should be p atm plus this delta p, right? That's what I'm talking about. I hope you understood that.